Next, we have Annabelle Wong from Max Planck.
Thank you for being here. I'm very happy to share with you our project on the effect of social context structure on vaccine impact. First, let's look at the pathogen we're interested in. Streptococcus pneumoniae are a type of bacteria that causes pneumonia and invasive diseases such as meningitis and sepsis. It can colonize the human nasopharynx for days without causing symptoms, and during this period of time, it can be transmitted, and that's why colonization is important for transmission. So there are different generations of pneumococcal conjugate vaccines, PCVs. In the year 2021 and 22, the latest one that got approved were PCV 15 and 20, and they cover up to 15 and 20 out of 100 identified serotypes. And these serotypes are classified based on the antigen on the capsule of the bacteria. These vaccines protect not only against diseases, but also against colonization among the vaccinated individuals, and that is the direct effect. Because of that, it also reduces the transmission in the population, and that's the indirect effect. So it also protects the people who are unvaccinated. After the vaccine was introduced, carriage with vaccine type indicated by the light blue line here has drastically reduced. But at the same time, the colonization with the non-vaccine targeted serotypes have increased. And this is the case we observed in the UK. It was also observed in other settings. For example, in a study conducted in Nigeria, where they looked at rural and urban settings, and in both children and adults, they also discovered this serotype replacement phenomenon. So it seems that when vaccine type removed, the non-vaccine type would take over, and leaving the overall carriage constant over time, as you can see by the gray line here. It would be interesting to understand why the vaccine type get eliminated faster in some populations than in others. So what are the differences in these populations? We thought of one potential factor among many others, and that is the social contact structure. And by social contact structure, we mean the number of contacts between different age groups. Could this be part of the reason of vaccine type being eliminated faster in one population than another? So we developed a transmission model tracking the susceptible, the colonized by vaccine type, colonized by non-vaccine type, and also co-colonized. The force of infection for vaccine type and non-vaccine type in age group I depends on the susceptibility parameter beta, the contact rate between the age group I and age group J, and also the total number of individuals colonized by a given serotype in the age group J. Note that all colonizations were cleared at an age-specific rate, gamma, and this makes the model neutral, as proposed by Lipsitch et al., such that there is no hidden mechanism for stable coexistence of the two serotypes at equilibrium. And this way, we can fix the initial colonization prevalence to any level, and we can be sure that the dynamics in the simulations are due to the vaccine that we introduce and not due to the hidden mechanism in the model. And here I just want to show you what the simulated prevalence would look like in a neutral versus non-neutral model. And the four compartments are duplicated for vaccinated individuals. So here everything stays the same, except for the force of infection for the vaccine type would be modified by a fraction, 1 minus VE, where VE stands for vaccine efficacy against colonization. To add realism, we allow the vaccine conferred protection against colonization to wane over time. We also incorporated age structure into the model, and here the newborns are fully unvaccinated. As they moved to the age of 1, a percentage of them received the vaccine while the rest remained unvaccinated. After the age of 1, the individuals would move to the next year of age, and there is no further vaccination. The parameters were either taken from the literature, fitted to observed carrier age surveys or assumed with a value and tested using a range in the sensitivity analysis. And so first we wanted to verify our model against observed vaccine type elimination dynamics in children. To do that, we took the carrier age survey data from children in four locations, France, the UK, Alaska, and Massachusetts, US. And we used the location-specific parameter sets, including vaccine coverage, the overall prevalence of colonization, and also the initial ratio of vaccine type versus non-vaccine type colonization. And then we estimated the susceptibility parameter to achieve the pre-vaccine prevalence of colonization in the age group, as indicated by the red circle there. And for Massachusetts, we actually don't have a data point before the introduction of the vaccine as indicated by the dashed line. But because the first data point was so close to the time of introduction, it was only a few months after, so we still included in the analysis. Then we simulated the transmission dynamics with the introduction of the vaccine using a range of value for the vaccine efficacy against colonization taken from a cluster randomized controlled trial. In general, our model reproduced the real-life dynamics of VT decline over time in children after the introduction of the vaccine, except for France, in which the decline seems to have started before what our model predicted. And we think it could be due to the availability of the PCVs in the private market before it was officially introduced in the National Childhood Immunization Program. And to see the effect of the contact structure, we simulated the transmission using inferred contact matrices from 34 countries published by Mistry et al. And in their paper, they built the synthetic contact networks based on census data and also social demographic surveys. And then they used these synthetic networks to derive the contact matrices. And then we measure the time to elimination, which we define as the time between the introduction of the vaccine as indicated by the dashed line, and also the time point at which the vaccine type carriage has dropped to 5% of its initial value. And just by varying the contact matrices, we arrive at a range of time to elimination between 3.8 to 6 years in age group 0. Which reflects the indirect effect here because it is a fully unvaccinated age group. Among the parameters tested using a range of realistic values, vaccine efficacy and coverage had the biggest effect on time to elimination. And looking at 7 contact matrices here, increasing the vaccine efficacy from 33 to 77%, which corresponds to the lower and upper confidence limit from the clinical trial information. And under a scenario with 90% vaccine coverage, we can see a 2 to 2.5 years of reduction in the time to elimination. That is, in the right panel. And when the coverage is lower, around 50%, this reduction is actually even more pronounced. Then we want to look at what precisely about a contact matrix that influences the time to elimination. But this 85 times 85 matrix is quite high dimensional. Is there a method, is there a way to reduce it so that we can just use a single measure? And inspired by a study that uses summarizing features of contact matrices in Italy to explain the excess death due to COVID, we defined 2 features here. And the first one is total contact by age group. So here, for example, for age group B, the total contact would be the sum of all of the contacts in that age group divided by the size of that age group so that it is comparable across age groups. For example, age group A, which has a much smaller interval in terms of the span of age. And here is a descriptive plot of the total contact across age groups for all 34 countries, with a few countries highlighted to give you some context. And we notice very similar patterns over age groups among all of the countries. But there is quite a high variation, specifically in the youngest age group, children under 5. The second feature we looked at is assortativity. And here we define it as the proportion of within age group interaction out of the total contact in that age group. In a way, it is a measure of how much people like to hang out with their own group, their own age group. And we did the same descriptive plot here. We've seen much more variations across the countries. For example, India, as indicated by the light blue point and line here, has an initial rise from young age to a peak at around late teens, and then it drops gradually towards older age. But you also have countries like Canada, as indicated by the light green point and line there, which has relatively stable assortativity throughout lifetime. To see the relationship between these features and the time to elimination, we plotted the time to elimination on the y-axis, the standardized total contact on the x-axis, and then we use a color scale to represent the second feature, standardized assortativity. And we noticed a correlation between these two features and the time to elimination only in the children age group, in children under 5, but not in other age groups. And then when we put the two features into a linear regression model, these two predictors actually explained 95% of the variability in the time to elimination in that age group. And to sum up, our model recapitulated the vaccine type colonization decline in children in the real world, except with some discrepancy in France. And contact matrices alone actually can lead to different time to elimination already. And among the parameters that we have tested, vaccine factors seem to be the most influential one in terms of time to elimination. And last, we found that the contact rate and assortativity in children under 5 to be key features for predicting the time to elimination. And with that, I would like to thank my lab, led by Mathieu Dominique de Celeste, and also my co-authors. And we already have a preprint. So if you're interested, please feel free to check it out. And if you have questions, you can also ask them right now. Thank you.
That was great. Thank you so much. Any questions?
Oh, thanks. I think this is really cool. I always love someone who can figure out that 2009 paper that just is so mind-boggling. I'm curious, like, so you're explaining this difference in elimination time that doesn't vary that much, right, between 3 and 6 years. I'm curious, are there other factors that you think could be driving the change in that time other than contact matrices? I don't know. I was just thinking about vaccine uptake timing, or right, there's like, I wonder if there's other factors that are at play here and whether you can eliminate any of them or demonstrate that they aren't the relevant factors. I don't know if any of that made sense, but.
Yeah, I think what you're asking is what other factors could play a role and maybe cause a more drastic time to elimination than what we have simulated here, right? And yeah, you're absolutely right that this small range of time to differences in the time to elimination is just caused by the contact matrices here. And I think in this study, we just want to show that actually this plays a role and it can be part of the reason. And definitely there are other factors that we have considered, but we haven't put it in there because in a way we wanted to do it one at a time so that you can see that, oh, it is not an array of different factors altogether. But in reality, that's probably the case, right? And other factors could be the initial prevalence of certain serotypes. For example, the PCVs, they were developed in higher income setting. And in these settings, actually the transmission pressure is already quite low. And they actually, the prevalence of serotypes are also different. So when you use these vaccine that targets the serotypes that are much more common in these higher income settings, would this be also as efficacious and as good in eliminating the feti in other settings. So I think that's also one of the factors. And the other factor is definitely the real life implementation of the vaccination program. For example, in one case, I think we didn't show it here, but in another study that we did in Mexico, for example, they first have a pilot rollout in a few regions that with particularly deprived children. And then later on, they decided to roll it out. But then that actually extended the rollout period to more than 2 years. And so I think those are more pragmatic factors that we also need to take into consideration when modeling.
Any other questions? I have a quick question. Do you think that the effective vaccine efficacy could be impacted by the contact matrices through the mechanism of repeated exposures?
You mean the vaccine efficacy against colonization or the total the impact?
And if in your models you fix the efficacies for each simulation scenario, right?
Yeah.
But that is a fixed efficacy from a trial, but effective efficacy might be lower because it's a leaky vaccine and there's repeated exposures. If the sorority is higher, you would assume that individuals who are unaffected might be exposed more often, so the effectiveness would be lower. Is that something that might affect the overall impact?
Great question. So we actually didn't consider that in this work, but actually you're absolutely right that there is uncertainty and there are more things to consider for the vaccine efficacy. So one thing to consider is that we actually use this, we group all of the vaccine type together here, and we say, okay, this vaccine has this fixed efficacy against all of the vaccine type, but that is probably not likely the case in real world scenario because this vaccine may be more efficacious against serotype, let's say 19A versus serotype 3, which are the included serotypes there. And so there is heterogeneity in terms of the efficacy targeting the serotype itself. And then second dimension would be for different populations. So for example, I think a group in Oxford led by Marine Voisey, I think they looked at the efficacy or maybe field efficacy, which would be effectiveness in high transmission setting versus low transmission setting. And it seems that you need to elicit higher antibody level to achieve the same level of protection. So that's probably what you were commenting on as well. But yeah, but we didn't consider it here. It's probably one of the limitations.
I thought it was a great talk. Any last questions before we finish up?
I'm gonna apologize in advance because this is kind of tangential, and so you might not know. But so at the very beginning, you showed changes in the breakdown of prevalence between the different strains. And so my first kind of question is, does the actual prevalence level change? We're just switching out strains, or is there actually a decrease overall? And then to kind of go on to that, if the prevalence isn't changing, does this mean the vaccine's a failure, or are we eliminating virulent strains and replacing them with less virulent strains?
Okay, great questions. And so I'll first answer the first question. I don't know if I can go back to the slides very quickly. So to answer your first question, the overall carriage actually remained quite similar. I think it's this one here, the great line here. And that leads to your second question. Does it mean that this vaccine is a failure? I think that would not be the case. And actually, it's also proven not the case because you do eliminated or prevented the colonization with some very, not virulence, but with the serotypes that has a high tendency to become invasive diseases and to cause actual problems. And so by removing that, there is still a big benefit in the population. I guess right now the discussion is more like, oh, if we keep expanding the valency, at what point would it become not so useful anymore? And also, I think that this is also maybe perhaps tangential, but I think important in this application question is that as you increase the valency, would it also cause the antibody level or immunogenicity against each serotype to be slightly lower? Actually, that's also part of the work that we are interested in looking into.
And so a follow-up question, would that mean that at some point you don't necessarily need the vaccine because you've displaced the strains you're worried about and the natural competition will keep it low? Or
Say that again.
So is there any evidence that strain competition itself will keep kind of these ones we've been vaccinated against out once they're out, right? That if you do a vaccine campaign, you kind of replace what's colonized, and then you're happy just to keep that, and what's colonized will keep out these dangerous strains.
So there have been work that show that together with inter-strain competitions, the vaccine actually achieved a higher than expected efficacy. So that's one aspect. But the other aspect is that I think there is a trade-off. So if you achieve a high enough vaccine coverage, you probably, like what you said, you would be able to maintain in this population a very low transmission and colonization. But then the other aspect is also what I just mentioned. When you increase the valency, would you also reduce some of that competition? When you remove those competition, would some eliminated serotype comes back? That's one thing. And the other thing is that as you increase valency, would the immunogenicity still be sufficient? So yeah, complex problems.
Great, thank you again. Can we thank all the speakers again?